All right, hi everyone. In this video, we are going to go through the lecture material for section 14.9. Just a reminder, due Monday, you have 14.6 and 14.7 for homework, and then test 2 is coming up next Friday on chapter 14. The overview is already in Blackboard. All right, so let's get started here. We are looking at section 14.9, and 14.9 is called Lagrange multipliers. Lagrange is the name that you may not know how to say. And in this, so we'll start with just kind of the general theory behind what's going on, and then more procedurally, what do we actually do, and then we'll look at a couple of examples from the section. So first, the theory. We're doing kind of what we did similar to in the last section, finding a maximum and minimum value on a function, but not just the maximum and minimum values on the function. So we've got like our surface z equals f of x, y. That's this like gray surface here. And we're not just trying to maximize or minimize that function. We're looking at a specific curve c on that function. So this red curve, what are its highest or its lowest points on the surface? So we've got the constraint curve that's on the xy plane, and that's the where I am on the surface. So that's kind of the idea visually of what we're trying to accomplish here. Given a function and a constraint, what are the highest or lowest values on the function on the constraint? Okay, another visual example of what we're looking at, we've got this paraboloid over here. F of xy equals x squared plus y squared minus 2x plus 2y plus 5. So that's just our paraboloid. And we're not looking for the highest or lowest points on the paraboloid. We're looking for the highest and lowest points on the paraboloid, but on this constraint curve, this ellipse. So in the it's a circle. In the xy plane, we have x squared plus y squared equals 4. What does that look like on the paraboloid? It becomes an ellipse when it is up on when the z coordinates are up on the paraboloid. And we can kind of see visually the highest point is up here, the lowest point is down there. We've got level curves over here on the right. This happens to be at the point negative radical 2 comma radical 2 in the xy plane. But so the goal in this section is to be able to find those points. Given a function and a constraint, what are the maximum and minimum values on the function given the constraint? This next slide here, we have another visual. This kind of gets more at where the formula comes from. So we have these green level curves of our function in the xy plane, and then the constraint is the red curve. And we can look at any point on the red curve. So here, I'll mark this point here. At that point there, we can find our vector tangent to the curve, and we could also compute the gradient at that point. Similarly, as I come over here, we can compute, at this point here, we can compute the tangent vector at that point, and then we could also compute the gradient at that point. But over here, at this point that they've got marked AB, we can find we find that the gradient on the constraint and the gradient on the function happen to be pointing in the same direction. Not necessarily the same length, but they are both pointing in the same direction. So those two blue vectors that point in the same direction but aren't necessarily the same length are really where our formula on the next slide comes from. And here's the main theorem from this section. It's called the parallel gradients or ballpark theorem. We have f as a differentiable function on a region in R2 that contains our curve c. C, again, is the constraint curve. F has an extreme value on c at a point P, AB on c. Then the gradient of f at that point is orthogonal to the line tangent to c at P, assuming the gradient of g is not 0. It follows there is a real number lambda called a Lagrange multiplier such that the gradient of f at AB is equal to lambda times the gradient of g at AB. So that sounds like a whole bunch of junk, but the main formula here that I'm going to underline says that the gradient of f and the gradient of g at the point AB, at this maximum or this extreme value, are equal to each other except for some constant, and we use this we use a real number, we use the variable lambda as that constant. So to go back, if I were to go back to the previous slide, right, that just says that they're equal to each other but not necessarily the same length, or they point in the same direction but not necessarily the same length. And the reason that they're calling this the ballpark theorem and comparing it to this, giving it this baseball analogy, is, remember, as at just like in the last slide, at each of these points, as I move around my constraint curve C, we can compute the tangent vector, but only at one of them is that tangent vector also the highest point on my function, and that's at that point P that we've got here. So we're kind of like looking around the outfield at a ballpark. That's why they compare it to that. Okay, so procedurally, how do we actually do these problems and maximize our function given a constraint? This slide has the approach that you take. We're given a function f, and we're given a function g. Okay, f is the objective function, g is the constraint where you are on the surface. We compute both gradients, the gradient of f, the gradient of g, and set them equal to each other with this lambda. Okay, so that's the gradient of f of xy is equal to lambda times the gradient of g of xy. And we also take our g of xy equal to 0, the original g function, the constraint. And then among the values xy that we find in step 1, so we'll do a whole bunch of algebraic manipulations in that step 1, we select the largest and smallest corresponding function values. So whatever x and y coordinates we get, we substitute them into f. The highest one is the maximum, the lowest one is the minimum. Okay, so step 1 has a whole bunch of algebra. Step 2 is plug it into the original function and see what happens. Let's look now at our first example. So we have our objective function, f of xy is equal to 2x squared plus y squared plus 2, and our constraint, g of xy is x squared plus 4y squared minus 4 equals 0. Okay, so you can see our f function, we're on a paraboloid, that's our surface, and our g function is an ellipse. So we're looking at an ellipse on a paraboloid. And so to start with, we're going to compute the gradient of f first. The gradient of f is equal to, in this case, we get 4x and 2y. The gradient of g is equal to 2x and 8y. All right, step 1, there you go. Well, there's a whole lot more in step 1 from the previous slide, but that's the first piece. Compute the two gradients. Now, we take our x components from these vectors, the f sub x's, and set them equal to each other. So 4x is equal to lambda times 2x, and then we take our y components from these vectors and set them equal to each other. And we get 2y equals lambda times 8y. And additionally, I'm going to rewrite my g constraint down here with this step. So we rewrite x squared plus 4y squared minus 4 equals 0. Okay, so now we take these three equations, the first one from the x's in the gradient, second one from the y's in the gradient, and the third one, the original constraint, and we've got to manipulate these somehow to solve and get some solutions x and y. Okay, so I'm just going to start with number 1 and kind of see what happens. Well, I see that I've got x's on both sides. So let's say I start out by subtracting that x lambda times 2x. So we go 4x minus lambda times 2x equals 0. Okay, so now I've got this equation equal to 0. So I don't know, can I factor? Let's see, if I take 2x out from both terms, I'm left with 2 minus lambda is equal to 0. All right, so that gives me solutions of x equals 0 or lambda is equal to 2. Let's take the same approach with our second equation here. 2y minus lambda times 8y equals 0. Factoring a 2y out, we're left with 1 minus 4 lambda equals 0. So now I could say I've got y equal to 0 or lambda equal to 1/4. Okay, so you may be thinking at this point, all right, does that mean that 0, 0 is one of the solutions? Not the case. What we do now is we take this first solution from equation 1, x equals 0, and now I'm going to go over here and plug it into the constraint. If x is 0, then we have 0 squared plus 4y squared minus 4 equals 0. Or solving that, we get y squared is equal to 1, or y is plus or minus 1. Okay, so that is one of our possible maximums or minimums on the constraint. We have a point of 0, comma, plus or minus 1. Okay, so you take your solutions that you get from these Lagrange equations and substitute maybe into the constraint and see what your other coordinate is. If I do the same thing with y equal to 0, let's see what happens there. We have x squared minus 4 is equal to 0, or x is plus or minus 2. And that gives me another point on my surface and on the constraint. That would be plus or minus 2, comma, 0. Okay, so in this example, you might be possibly wondering at this point, well, what do you do with the lambda equals 2, the lambda equals 1/4? At this point, there's not a whole lot that I need to do with them. I've got my possible max-min points. You may run into a different problem where you need to use lambda in order to solve one of your other equations. So just the way that this one worked out, we got lambda equals 2, lambda equals 1/4, but there's not really anything that you need to do with that in this example. Okay, so our next step now is that step 2 from the other slide, where we now need to take our points and substitute into the original function. So I'm going to take my 0, comma, plus or minus 1 and evaluate that in my function f. And I know that it doesn't matter whether I substitute in positive 1 or negative 1, because f is the x and the y are both squared, so they're going to be positive. And if you substitute 1 or negative 1 into the original function, you get 3. So 2 times 0 squared plus 1 squared plus 2 is 3. And if you substitute f of plus or minus 2, comma 0 into the original function, 2 times 2 squared plus 0 plus 2, you get 10. All right, and so what that means is that 0, comma, plus or minus 1 is a minimum, and plus or minus 2, comma 0 is a maximum. Okay, and those are the highest and lowest points on the paraboloid, but as I move around that ellipse C, x squared plus 4y squared minus 4 equals 0. This next slide, we're looking at the function, the paraboloid, 2x squared plus y squared plus 2, and then we've got our constraint, x squared plus 4y squared minus 4 equals 0, showing that in the xy plane, and then on the surface. And you can see that up here, I've got the two highest points on the surface on the constraint, and over here I've got the two lowest points on the surface on the constraint. So that ellipse, right, it moves in the xy plane. It's just this red ellipse down there, but as the points on that red ellipse move on the paraboloid, they go up and down, very much like a roller coaster, right? Okay, and so we get 2 points that are really low, the lowest two, and 2 points that are high. Okay, so now we get into the really fun stuff. Now we're going to look at Lagrange multipliers with 3 variables. So our f and our g functions are going to be in terms of the variables x, y, and z. So our constraint is g of x, y, and z is equal to 0, and our f function also is in 3 variables. So we compute the gradient of f and the gradient of g, which are both going to have three components. We take our partial derivative with respect to x, then with respect to y, then with respect to z, and set them equal to each other with the lambda on the right-hand side. So we're actually going to end up in these problems with four different equations: a partial x equation, a partial y equation, a partial z equation, and the constraint. Okay, so whole bunch of algebraic manipulation that we're going to need to do. And then step 2 is whatever points we get in step 1, we substitute into the original function. So step 2 is like the easy step where you just plug it in. Step 1 has like 57 steps contained within it. That's lots of algebra in there. All right, so in this last example from this section, we're looking at, we're trying to find the least distance between a point P, 340, and the surface of this cone z equals x squared plus y squared. Actually, before we start this problem, what I want you to do, if you want to earn, let's say, 4 bonus points on your most recent quiz, on your homework that you're turning in Monday, after the last problem, write the sentence, "I watched the whole video." Nothing else. That's all you got to do. 4 bonus points on your quiz. Okay, back to the problem. So we've got to minimize this distance, find the smallest distance from our point P onto the cone. So I've got a terrible sketch here. You can take a look at it, but that's kind of the visual representation of what we're looking at. This cone has a cone above the XY plane and below the XY plane, so we should anticipate getting two solutions, one for each part of the cone. And so what we're going to do is we're first going to write down the distance formula, and this distance formula is a function of x, y, and z, because we have x, y, and z coordinates, and it looks like this. It's the square root of x minus 3 squared plus y minus 4 squared plus z minus 0 squared, so just z. That is our objective function, the function that we are trying to minimize, find the least distance. Then our subject to, the constraint in this case, is the cone z equals x squared plus y squared. So we're going to write that constraint, g, as a function of x, y, and z, is equal to x squared plus y squared minus z squared equals 0. So now we have two functions, objective and constraint, just like we did before. The next piece, the next step, is we're going to compute both of our gradients. But before we do the gradients, we're going to make one tweak to our function d here, the distance formula. And the rationale is if we have a point of value that minimizes d squared, it also minimizes d. So what we can do and still be mathematically accurate but have a much easier time doing the problem is we can square both sides of this equation. D of xyz squared is equal to x minus 3 squared plus y minus 4 squared plus z squared. So we square both sides, and then we can compute the gradient. And again, the partial derivatives just are significantly easier, and we don't have to worry about dealing with this gigantic chain rule involved here. Okay, so now we'll go ahead and compute our gradient for that d function. So there are 3 partial derivatives we need to take. Our f sub x is 2 times x minus 3 to the first power, and we're going to set that equal to f sub x of the other, or g sub x, excuse me, is equal to lambda times 2x. Then we take and compute our f sub y. That would be 2 times y minus 4 to the first power is equal to g sub y is 2y. Finally, our f sub z, or d sub z, I guess in this case, is 2z, and set that equal to lambda times negative 2z. Let's throw that in parentheses. There we go. Okay, so we've got those 3 equations from the gradient, from computing the gradient, and I'm also going to rewrite my constraint equation. X squared plus y squared minus z squared is equal to 0. There, we've got 4 equations. solve them. Now we get to the fun algebra part of the problem. Okay, so taking a look at each of these four equations, where the heck do I start? There's so much to look at. What I'm going to focus on is which one looks the shortest, the easiest that we might be able to actually solve. And that ends up being this equation right here, our z equation. So if we have 2z equals negative 2 lambda z, well, the first thing I can do is I can cancel out a 2 on both sides. Or divide both sides by 2. And then what I want to do is I want to take z plus lambda z equals 0, so add that term to both sides. And then I can factor z times 1 plus lambda equals 0, and we get two solutions there. Z equals 0 or lambda equals negative 1. Now take my first solution, z equals 0. If z equals 0, let's say I try to substitute that into the constraint for z. Well, that would basically imply that x and y both have to be 0 also. If z is 0, then I have x squared plus y squared equals 0, so I wouldn't get another solution out of, or I wouldn't get a valid solution out of that, because it would not satisfy this equation or this equation. That's kind of the rationale there. If z is 0, then x and y both have to be 0, and that wouldn't work in the other two equations. They all have to work together. Right? All this, whatever solutions we come up with has to satisfy all of the equations. Okay, so now let's take our lambda equals negative 1. If lambda equals negative 1, then I can rewrite this x equation over here. First, I'll divide out the 2, and so I have x minus 3 is equal to negative 1 times x. And that's going to give me a solution. I get 2x equals positive 3, so x is 3 halves, or 1 1/2. I just realized I have an error in my y equation that I didn't catch earlier, so I'm just going to go ahead and squeeze it in now. If you caught it earlier, that's great. If you've been confused for the past few minutes, I apologize. That equation should have had a lambda inside of it. Doesn't look good like that. That equation should have had lambda. So 2 times y minus 4 equals lambda times 2y. All right, so our next piece here, we're going to take lambda equals negative 1, substitute it into our y equation. I can also strike the 2 out on both sides of my y equation, and I have y minus 4 equals negative 1 times y. So 2y equals positive 4, y is equal to 2. All right, so this is progress. We have an x solution, we have a y solution coming from each of those first two equations. The third equation gave us z equals 0. That doesn't work. And so now we go over to our constraint, and if I substitute 3 halves for x, and I substitute 2 for y, we can then solve for z and get our third coordinate. Simplifying that, we would have 9/4 plus 4 is equal to z squared, and I would, what would that be? 9/4 plus 16/4 is 25/4 is equal to z squared. So then z would be plus or minus 5 halves, 5 over 2. So there we get 2 points. How about that? Our first coordinate is 3 halves, comma 2, comma 5 halves, and our second coordinate is 3 halves, comma 2, comma negative 5 halves. All right, but there is one more step. So all of that work, that was step 1 from the previous slide. But the last piece that we've got to do is we need to take and evaluate these 2 points in our original function. So plugging each of these into our d function, what does that give us? I'm not going to go through the calculation work here, but you would get, let's see, you would get for both of them, you would get 5 over radical 2 for both points. If you go into the original d, if you go into d squared, you get what, 25 halves. Okay, so because that number is the same, it actually means that those points both minimize the distance from the point or they're the shortest, the closest point to 340 on the cone. Okay, so that was a really long